The objective of this topic is to develop a technical understanding of the welding characteristics of non-ferrous materials other than aluminum as they apply to the gas metal arc process. One very important characteristic of gas metal arc welding is its versatility with welding many different kinds of non-ferrous metals, giving results of equal quality to those performed on steel. Although the process works well with many non-ferrous metals, the most frequently encountered applications, beside aluminum, are for copper, magnesium, nickel, and their respective alloys. Of these non-ferrous metals, none is more widely used by industry than copper. It can be alloyed with many compounds to produce over 300 different alloy types suited for particular applications. Some of the common alloying metals are zinc, lead, tin, silicon, and aluminum. Copper and its alloys are frequently used by industry to produce bearings, electrical wiring, and parts for food processing industries. Copper and aluminum share many similar properties which affect their weldability. Perhaps the most important characteristic of copper is its rate of electrical and thermal conductivity, the highest of all known metals. Copper's electrical conductivity rate is over a third greater than aluminum, which makes copper especially useful for transformer wiring, bus bars, and power cables. However, because of its high rate of thermal expansion, welds made with copper often crack. This happens because the base metal in the weld area expands at such a rapid rate that the joint shrinks. During cooling, the metal re-expands and causes the weld to crack away from the base metal. Also, copper has a low melting point, which combines with its rapid thermal conductivity to create problems with melt-through. To avoid this problem, both the travel speed and the amperage setting must be increased. Two other problems encountered when welding copper is brittleness at high temperatures, often the cause of hot cracking, and its very fluid weld puddle, which makes vertical and overhead position welding difficult. The two processes most normally used for copper welding are gas metal arc and gas tungsten arc. Of these two, the gas metal arc process is favored for thicker weldments because it produces less distortion, has a higher deposition rate, and can be used in all welding positions. To help reduce hot cracking in copper, the metal is preheated before welding. The amount of preheat depends on the size of the weldment. The temperature can range anywhere from 250 to 1,000 degrees Fahrenheit. Brass is a copper alloy frequently encountered in industry. It is created by mixing copper with zinc, lead, or tin, with zinc being the major component of the alloy. Most types of brass are weldable with gas metal arc, with the exception of brass containing large amounts of lead. Lead creates problems with porosity and cracking due to its dissimilar properties with copper. On the other hand, brass containing zinc or tin is easily welded, provided that the weldment is preheated to about 400 degrees Fahrenheit in order to avoid cracking. These joints should have enough of an opening to allow sufficient penetration. Another caution when welding brass alloyed with zinc is to lower the amperage or reduce the amount of preheat to prevent the zinc from vaporizing and ruining the weld. The opposite case is encountered when welding bronze, an alloy of copper and high amounts of tin. Here, current and travel speed must be increased because bronze has a high thermal conductivity similar to aluminum and is prone to heat cracking. Bronze joints require larger openings to provide penetration rather than relying on arc action in order to prevent heat from building up and creating cracks. To summarize, although aluminum and copper are non-ferrous metals with many similarities, they must be welded differently because of copper's higher rate of thermal conductivity. Successful welding on copper and its alloys is best accomplished by increasing amperage, using large diameter electrode wires, increasing electrode feed rates, and preheating the base metal. Another non-ferrous metal frequently welded with the gas metal arc process is magnesium, which looks very much like aluminum, but requires different welding procedures and techniques. It is one of the lightest structural materials available, with only 2/3 the weight of aluminum and 1/4 the weight of steel. Although light in weight, magnesium is strong. Its weight-to-strength ratio makes it particularly useful in the aircraft industry and for fabricating hand tools. By alloying magnesium with zinc, aluminum, manganese, or zirconium, parts may be fabricated that are equal in strength to low-carbon steel, yet only 1/4 as heavy. Adding to its versatility, magnesium is weldable by arc or resistance processes, as well as oxy-fuel. In many ways, magnesium and aluminum share similar properties. Both metals tend to form oxide coatings which serve to protect against corrosion, but must be removed before welding can begin. Their thermal conductivity is similar too, although magnesium does not conduct heat quite as well. However, magnesium and aluminum share the same high rate of thermal expansion. Their melting points are just as low too, which makes it necessary to increase travel and wire feed speeds. In most cases, magnesium is welded with the same equipment used for welding aluminum. It is necessary, however, to increase the wire speed beyond that of aluminum to compensate for the higher melt-off rate of magnesium electrodes. Short-circuiting transfer produces the best results on magnesium up to 3/16 of an inch thick. For thicker sections, a spray transfer is recommended. Whichever transfer is used, the proper polarity is direct current electrode positive, also called reverse polarity. Shielding gases can be pure argon or a mixture of helium and argon. As stated earlier, the oxide coating must be removed before welding in the same manner as aluminum. In regard to nickel and nickel-based alloys, a number of types are weldable with the gas metal arc process. These alloys are generally identified by a trade name, for example, Monel, an alloy of nickel and copper, Inconel, a nickel-chromium alloy, and Incalloy, a blend of nickel, chromium, and iron. Nickel alloys have good corrosion resistance and are used in the chemical and food processing industries. Nickel-based filler metal is used to braze cast iron because nickel combines with carbon in the iron to prevent braze welds from cracking. Like aluminum and magnesium, nickel will develop an oxide coating which must be removed prior to welding operations. Alloys of nickel have a tendency to become brittle at welding temperatures if any lead, sulfur, or phosphorus are present in the weld area. Nickel behaves much like stainless steel in regard to melting point, thermal expansion, and conductivity, although the conductivity rate is rather low when compared to aluminum. Welding procedures for gas metal arc and nickel alloys are similar to those used for austenitic stainless steels. Direct current electrode positive and a shielding gas of argon or an argon-helium mixture produce the best result on nickel alloys. Joint preparation requires special attention, however, since penetration is minimal. Groove angles and root openings should be increased by 40%. Non-ferrous castings and cast iron are special welding cases that require equally special techniques, since castings of any sort tend to be very brittle and often retain dissolved gases from the casting process that can contaminate welds and cause porosity or inclusions. To work with these materials, specialized procedures must be developed and rigorously followed, particularly in the areas of filler and base metal matching, thorough cleaning, and the application of preheating and post-heating processes. In conclusion, Gas metal arc welding is adaptable to many non-ferrous metals, and quality welds can be made on a variety of materials as long as the proper welding procedures and techniques are followed, and the filler metal is carefully matched to the base metal.